This question is asking for the major organic product. So the first thing to note is we have these two ionic bonds between sodium and sulfur. And because we're doing the reaction in a polar solvent, we know that we can have the sodium ions dissociate, leaving us with this guy, which has negative charges on each sulfur atom. And we know that because sulfur is in the same group as oxygen, so it has the same number of valence electrons. And right away it should pop out that this molecule would make a very good nucleophile, and it can also function as a base. So to figure out what's going to happen, we look at what we are reacting with, which is this haloalkane. And this molecule has these two electrophilic carbons, and they're attached to a good leaving group. We know that the bromide anion can leave in a polar solvent, and it's relatively stable. So the presence of these electrophilic carbons with a good leaving group is a pretty good indication that we're going to have some type of substitution or elimination reaction. And to figure out which one, I'm just going to write them all out, and we can do a process of elimination. Okay, so when you're doing these types of problems, you need to first look at the electrophilic carbon with the leaving group on it and determine whether it's primary or secondary or whatever, because that's one of the key things in deciding which type of reaction you're going to have. And here we have primary carbon, so we're only attached to one carbon. So right away we can rule out the E1 and Sn1 mechanisms, and we know that because the first step in those mechanisms is the formation of a carbocation, and you can't form a carbocation on a primary carbon. It just wouldn't be stable enough. You would need at least a secondary carbon so it can be stabilized from hyperconjugation. Okay, what else? In order to have an E2 reaction on a primary carbon, you need to have a very bulky base, which we don't have here. Bulky base would be something like tert butoxide or LDA. I guess I'll draw tert butoxide now that I said that. Or LDA. And oh yeah, or the other thing that can happen to cause an E2 reaction is with a normal base, you would have a lot of branching on the adjacent carbon to the carbon that is attached to the leaving group. And we don't have that in this case. The adjacent carbon's only attached to the one bromo group. So because of that, we're not going to have an E2 reaction. And the only thing left is an Sn2 reaction. So that's what we're going to do. So I'll redraw this guy over here. And what we have is just your standard Sn2 reaction. The nucleophile attacks the electrophilic carbon, and we kick off the leaving group. And we now have a neutral charge on the sulfur. 1, 2, bromine. And the reaction's not done yet because we still have the same conditions present that drove the first reaction, which is we have this nucleophilic negatively charged sulfur, and we have an electrophilic carbon that has a good leaving group attached to it. So what we have now is an intramolecular reaction where it's another Sn2 reaction, and that's going to leave us with a cyclic molecule. So in order to draw that, I need to first figure out how many members are going to be in the ring, so I know whether to draw a hexagon or a pentagon or whatever the other ones are called. So we have this carbon, so 1, 2, 3, 4, 5, 6, so we're going to have a hexagon. So sulfur, then 2 carbons, back to a sulfur, 2 more carbons, and then back to our original sulfur. So I'll draw some lone pairs for you. So this would be the major organic product. And I guess I'll also draw the anion. And we also have the 2 sodium ions from the dissociation step. And that would be the answer for this problem.